Hello. Oh, okay. Good afternoon, ladies and gentlemen. My name is Anna Hulda Ólafsdóttir and I am the head of the National Knowledge Center on Climate Change Adaptation. All right. Is it better? At the Icelandic Met Office. I'll be guiding you through this event today, and I want to welcome you to this event, the message on the cryosphere. The main focus of the event is to emphasize the importance of the cryosphere in the climate system and discuss the key messages prepared during the symposium Cryosphere 2022, which was held in Reykjavik late in August this year. The focus will also be on the pathways that will help prevent the global impacts resulting from melting glaciers and ice caps, ice sheet instability, and feedbacks due to reduction in Arctic sea ice cover. The event will consist of 7 presentations, followed by a panel discussion. The presentations will cover summaries given in concluding session at the Cryosphere 2022, and additional insights prepared by speakers at the symposium. Since I have a quite packed schedule, I'd like to start by welcoming our first speaker today, no other than Svandís Svavarsdóttir. She is the Icelandic Minister of Food, Agriculture and Fisheries. She is also the former Minister of the Environment and Natural Resources, Minister of Environment and Minister of Health. She has been involved in Icelandic politics for a long time, and we are very happy and lucky to have her with us here today. Thank you.
Dear guests, it's a great pleasure to be with you here today and to participate in this event on cryosphere, a phenomenon which probably has received too little attention, and now it is for the wrong reasons. It is disappearing. Science tells us that our climate is getting warmer. The various components of the cryosphere will continue to shrink and melt. The cryosphere is the part of the Earth's climate system that includes solid precipitation, snow, sea ice, lake and river ice, icebergs, glaciers and ice caps, ice sheets, ice shelves, permafrost and seasonally frozen ground. All those components are vulnerable to the impact of global warming. Changes in the cryosphere can lead to increased flood hazards, and they can also cause irreversible impact to biodiversity. For example, disappearing glaciers and sea ice affect ecosystems by changing habitats of vulnerable species. In different parts of the world, ongoing changes in the cryosphere are impacting various sectors of society: agriculture, transportation, security, hydropower, fisheries, and recreation. Coming from Iceland, we know that snow and ice can affect our life and make it difficult and sometimes even dangerous. But we also know that people benefit greatly from the cryosphere, and it plays a large part in the overall health of our planet through its effects within the climate system. The cryosphere has sometimes been likened to the canary in the coal mine because it displays clearly many of the negative effects of global warming. If we succeed in reducing greenhouse gas emissions and thereby stop atmospheric warming beyond the limits set by the Paris Agreement, we will hopefully, in a few decades from now, see a recovery of the frozen parts of our planet, which play an important part in balancing the entire Earth system. An important step towards basing our wisdom on what science brings is to build a bridge, a functional highway even, between scientists, practitioners, and the operational institutions. We are here to connect science, experience, and policy, which is the only way forward, and I hope we will have a fruitful discussion here today. Thank you.
Thank you, Svandís. Next, I will introduce Dr. Þorsteinn Þorsteinsson. He is a glaciologist at the Icelandic Met Office, and he will tell us about some new results from the North Atlantic region. Þorsteinn conducts annual observation of the mass balance of the Hofsjökull ice cap in central Iceland and participates in monitoring flood hazards from subglacial and proglacial lakes. He has led ice core drilling efforts on ice cap in Iceland and thermal drilling onto subglacial lakes beneath Vatnajökull. Þorsteinn, you can take the floor.
Thank you very much, Anna Hulda. Can you hear me?
Yes.
I'm trying to share my screen. Can you see my presentation?
We cannot see your screen though. I think it's coming. Yes.
Can you see it?
Yes, we can see it.
Good afternoon. My name is Thorsteinn. I'm speaking from Reykjavik. And I would like to tell you a little bit more about the Cryosphere 2022 symposium and give you some recent results from the North Atlantic region. And I will actually be looking a little bit further afield in my presentation. And I would like to acknowledge collaboration with several colleagues and their input. The symposium was held in the Harpa Conference Center in Reykjavik. It was held on the occasion of the 100th anniversary of the Icelandic Met Office, and the idea was to bring together scientists from all that are working on all components of the cryosphere, on glaciers and ice sheets and snow covers, sea ice, permafrost, lake ice, and river ice. And you can see from the logos that many of the key sort of organizations dealing with cryospheric research and data gathering, like the WMO and IGS and others, were represented one way or another. And the IGS is actually planning to put up a thematic volume of the Annals of Glaciology with contributions from the conference. The conference had more than 300 participants from 33 countries in 6 continents. You can see the breakdown of participant numbers by continent on the left. In the central part, you can see the names of different sessions or the sort of topics of different sessions, both plenary and sort of specialized parallel sessions that were held, including a session on humans in the cryosphere, the effects of changing climates, that the changes in the cryosphere resulting from global warming is having on human habitats, for example, up in the high north and elsewhere, high mountain areas. On the right, you can see the gender balance, which was fairly good at this conference. Then we succeeded in providing travel support for about 20 students coming mainly from countries far away through grants from the International Arctic Science Committee and other bodies. This is the lineup of speakers. You can see many major players here in fields of paleoclimate, ice sheet studies from IPCC, glacier mass balance studies, Arctic hydrology, third pole environment, and so on. If you're familiar with this field, you will know many of these people. And let's get straight to some results. This is from Kari Luojos at the Finnish Meteorological Institute from a paper that he and his colleagues published a couple of years ago on Northern Hemisphere snow cover. They have used their ground-based data and satellite data and modeling to create a better picture, a good picture of the seasonal snow mass and its variations in the Northern Hemisphere for a 39-year period, 1980 to 2018. And you can see the panel on the left shows actually the maximum in snow mass in these Northern Hemisphere regions. The whitish areas are the ones that receive most snow in this depiction here. And it's expressed in terms of snow water equivalent thickness in millimeters. On the right, you can see the trends, long-term trends, actually expressed as millimeters per decade. The bluish spots are the regions that receive where there has been an increase. The reddish spots indicate decrease. The overall change is a slightly decreasing trend in the total mass of snow in the Northern Hemisphere for this period. Not surprising. Of course, we increase precipitation to increase a little bit in a warmer climate, but a smaller part of that precipitation will fall as snow relative to rain. On to the next component, sea ice. The panel on the left, the upper one, displays the Arctic amplification that is already observed. This is a data set from the last 60 years. Mean temperatures over September, October, November, or temperature increase actually, displaying clearly what we all know by now, that the Arctic is warming faster than the rest of the planet, 3 times faster or so on average. And obviously this has an effect on the Arctic sea ice cover, not least in summer. And there's a clear downward trend, and it goes down below 4 million square kilometers, the sea ice cover in the Arctic Ocean in September. But the 2012 minimum has not been surpassed since then. So people are not talking about an ice-free Arctic in summer in 2030 by now. If you look at the recent IPCC projections on the right, you can see in the lower panel that all the models here that are dependent on different climate scenarios and emission scenarios, of course, none of them is preventing an ice-free Arctic Ocean by summer earlier than 2050 by now. Let's go to the largest ice mass in the Northern Hemisphere, the Greenland ice sheet. What has it been doing in the past decades? This is a data set from GEUS, the Geological Survey of Greenland and Denmark in Copenhagen. They have created this very interesting data sets from their data. They are using weather stations and to sort of measure, and then they also model the mass balance over the Greenland ice sheet. Only 2 years since 1987 have displayed positive mass balance, but the Greenland ice sheet is losing typically 100 to 300 gigatons per year through surface melting and calving. And we were getting used to figures of 300 to 400, but actually this year has a moderate mass loss of 84 gigatons. But the Greenland ice sheet has been actually the largest contributor to the meltwater component of sea level rise during this century. Neighboring Iceland is here to the east of Greenland. And what are the ice caps in our country doing? Hofsjökull in central Iceland is a very good indicator of what ice caps in Iceland are doing in general. We have 10% ice cover. We've lost 7% of the total volume of ice since 1995. You can see how the area of the Hofsjökull ice cap has diminished over the past century or so, from 1,000 to 800 square kilometers. We have a 35-year mass balance record. Only in 5 of these 35 years has there been mass gain, but mass loss during 30 of these years. And that's the general picture since 1995, with a few exceptions. However, in 2022, we had moderate mass loss, expressed as minus 0.3 meters water equivalent. We explain this by higher winter snowfall last winter, 20% over long-term average, and a cool summer in 2022. Here's another interesting data set from colleagues who have just published this. These are satellite data giving the velocities of ice flow in Iceland. On the ice caps, you can see the reddish and yellowish sort of branches. These are outlets from the main ice caps. Let's look at Vatnajökull, where we have the highest sort of velocities, coming up to 400 to 800 meters per year. We get the fastest flow in the central and lower regions of outlet glaciers with a high altitude range and a high snowfall. And these data can put to a variety of good use. If we look to the European main continent, what is happening there? This is the Helstugubrean in Norway. Data from Norway indicate that it has continued to recede during this year total retreat 1,200 meters since 1901. And in the European Alps, they had absolutely record loss of glacier ice, by minus 3-4 meters water equivalent. And by now, this is explained by little snowfall, Saharan dust, and persistent heat waves in Europe during summer. And I conclude with this slide here. The Cryosphere 2022's symposium was successful in highlighting the changes occurring in different components of the cryosphere. There was emphasis on the need for integrated monitoring systems, climate services, and early warning systems with respect to flooding and mass flows due to melting of cryosphere components. And the last points here, I just leave that for you to read, just reiterating the points I made on the last few slides. So with this, I thank you for your attention.
Thank you, Thorsteinn. Next, I will introduce Dr. Karen Alley. She was one of the key listeners at the conference. She is an assistant professor at the Department of Environment and Geography at the Center for Earth Observation Science at the University of Manitoba. She will be presenting pressing issues in the cryospheric science, scientific themes, and new results from the conference. Her research is part of the large glaciological community effort to understand how the world's glaciers and ice sheets are contributing to sea level rise in a warming climate. And her work has focused on the nature of melting beneath the floating ice shelves that fringe the Antarctic continent, which in turn modulates rates of ice delivery to the ocean.
Thank you so much for having me. It's a pleasure to be here. My name is Karen Alley. I'm a glaciologist at the University of Manitoba in Canada, and I had the pleasure of attending the Cryosphere 2022 conference, which took place at HARPA this past August. We had hundreds of scientists from all around the world, from every cryospheric subdiscipline you could think of, come together to share brand new scientific results, discuss the data, and really get into the nitty-gritty. It was a fabulous, fabulous week with lots of new exciting things happening. I was asked to be a key listener for the conference to try to, at the end, summarize the scientific results. Now, you can imagine in a 10-minute talk, there is no way that I can summarize all of the scientific results from the hundreds of talks that were given that week. But I did my best to pick out some themes, and that's what I want to share with you today. My hope is that I'll give some context for the kind of the state of the science that we learned from the Cryosphere 2022 conference. And then speakers that you'll hear in this session after me will give some context to how those concepts really apply to policy and society in the real world. So the first theme that became really clear in the Cryosphere 2022 conference was the idea of embracing new technologies and methodologies. A lot of these new ideas are related to collecting field data. We saw people using drones, using remotely operated surface and underwater vehicles, using fancy new instruments that you can put under underneath ice sheets or at the bottom of the ocean. Really, really cool stuff that allows us to collect data over larger areas at higher resolution and with more accuracy than we ever have before. But the other thing that we see these new technologies doing is really promoting safety and efficiency in the field. The cryospheric sciences, just like any field, is incredibly dependent on diversity, bringing in people who have different perspectives and will notice different things to help us understand the world around us. And by increasing safety and efficiency in the field, we make it a more accessible place. We're able to bring more people out doing field work and learning about all of these things that we have to observe. Another aspect of new technologies that we saw highlighted in a lot of the talks is use of new satellite data. It was not that many decades ago that we'd never seen a full picture of our ice sheets or of our sea ice extent. And now we have maybe even more data than we know how to do with. But I can tell you that we're making strides really, really fast on knowing what to do with all of those data. With the increase in satellite data availability, we're increasing our computing technologies, coming up with novel processing and analysis techniques, things like machine learning, to help us make sense of the tremendous amounts of data that as individual humans is hard to work with, but by applying all of these technologies, we can make sense of this. Along with these brand new methodologies, we saw a real commitment to continuing long-term records as well. Just because there are new methodologies doesn't mean that the old methodologies are obsolete. A lot of the processes that are really important in the cryosphere, in terms of cryospheric change in particular, happen on pretty long time scales. And in many cases, we're only just now getting really enough data that we can see those processes happening. And it's vital that we continue the longest records that we have so we can continue tracking these long-term processes. So we're seeing people who are continuing to use the traditional methods or incorporating new methods in to extend these long-term records so we can maintain this really important aspect of our data collection. The second theme that I think was particularly evident in this conference is a commitment to data standardization and sharing. Something as simple as making sure groups from around the world are using the same data formats, which make it easy for people to use data from all around the world, and then making those data sets freely available online is an incredibly important part of moving our community forward. Just like making our field, the fieldwork, more accessible, this also means that we're making the data that we've collected more accessible to people from every walk of life, from all over the world. We're allowing for more diversity and inclusivity in our field, which is likely to move us forward more quickly. We're seeing field projects that are committed to bringing disciplines together and bringing people together from different institutions and different nations, and data analysis projects and modelers who are doing the same thing. We have commitment to coming up with ways that people can run the same experiments with different models to be able to really analyze how those models are behaving in relation to each other and in relation to the data that we have to compare them against. Similar to our commitment to increasing the technologies that we're using in the field, we still need to think about what we've already done and how we can continue that. There's a lot of data out there that may have been collected before the internet or before there was a lot of data available on the internet, a lot of data sitting on people's hard drives or sitting in lab notebooks that isn't being used just because it isn't being widely shared. And so there's pieces of context that we could have available to us that is not currently available to us. So as scientists, as anybody collecting and analyzing data, we have a responsibility not only to work on those data ourselves, but to make sure that it becomes available to everybody in the field. The final theme that I heard a lot of in the presentations at the conference is being very careful with all of these new and exciting things that we have to work with. We have more data than we have ever had available to us before, but that doesn't mean that we don't have gaps in our data. We have more interesting models, more aspects included in our models than we've ever had before, but that doesn't mean that our models include everything that we need to be thinking about. A quote that I heard a lot of people using throughout the conference is, "All models are wrong, but some are useful." So that's what that's saying, is it's recognizing that we can do our best to include every physical process that we can think of, but we won't capture them all, right? And we can include every bit of validation data and everything that we can to get a three-dimensional picture of our world, but we're still not going to get it all. We're not going to be infinitely high resolution. something that we're probably never going to achieve. What we can do is make sure that we're including all of the relevant physical processes and be very careful and very honest with ourselves about whether our models are likely to be realistically representing the world based on those physical processes that we're likely to be able to include. This is just an example. We saw many examples during the conference, but this is a figure that I saw a lot of people using in their talks. This is sea level projections in the future from the Intergovernmental Panel on Climate Change 6th Assessment Report. And what you're seeing here is a group of lines. You can see my mouse, but a group of lines down low with some uncertainty bars around them. Those are really advanced, really well-vetted models. We have a really good idea of what those models are showing. We have worked really, really hard to quantify the uncertainty in those models. And we can see based on that where sea level projections are likely to be in 2100. But you'll notice there's also another dotted line that goes well above those models. And that line reflects the work by lots of scientists who have looked at the paleoclimate record and who have looked at the physics of the ice sheets and have said, hey, there are some other processes that might be relevant to our models that aren't yet included in many of those models. And so that gives us a sense that while the uncertainties in our models we understand very, very well, there might be other uncertainties that we're not including in all of our models that will be very important to future change. This doesn't negate the results that we have in these models. We can see these are all trending in the same direction. We know where we're headed here. We know sea levels are rising. We know the basic physics behind that. But it does tell us that we have to be very careful about emphasizing what we do know in our models, but being very realistic about what we still have to work on. And while we saw really, really exciting new results at the conference, really exciting breakthroughs that are helping us interpret things in new and significant ways, this also highlights that there are still big problems that we as a community need to solve in our field. I want to wrap up by just reflecting for a moment on what we as cryospheric scientists need to be doing in general. It is our responsibility to communicate our results clearly. We as scientists need to collect data. We need to objectively analyze our data. We need to report what the results of our data say. We do need to communicate that clearly, though, so that it can be acted on. And the way that I think we do this is that we form really close relationships with climate services organizations, such as the ones you're going to hear from momentarily. These are the people who can understand the science and put our science into a context where it can be applied to society and to policy. So with that, I will thank you again for your time, and I will turn it over to my colleagues who can make those kinds of.
Thank you, Karen. Next, I'll introduce Professor John Pomeroy. Professor Pomeroy is Director of Global Water Future Program, the largest university-led freshwater research project in the world. At the University of Saskatchewan, he is in Canada, Research Chair in the Water Resource and Climate Change, Distinguished Professor of Geography, and Director of USAC Center for Hydrology. His primary research interests are in cold regions, hydrology, and water quality, with an emphasis on snow processes and the development of novel observations and modeling techniques. Today, he will present to us the climate impacts on snow hydrology and permafrost in the circumpolar region.
Thank you so much, Anna. And I'm happy to be joining you today from Saskatoon, Canada, which is in the Treaty 6 territory, treaty signed with Indigenous people over a century ago, and also homeland of the Métis. I'll start to share my screen and then show you start the presentation. Here we are. So I'll speak on snow hydrology and permafrost in these regions, and start off by the climatic underline. That we know that cold regions are warming faster than the rest of the Earth, and as we go to higher and higher latitudes, the warming that has already occurred, of course, far exceeds the 1.1, 1.2 global average, and starts to approach 4 degrees Celsius of warming already since 1960. And so mid-latitude countries such as much of Canada, Scandinavia are warming at twice the global average. The further north parts of these countries are warming at 3 times the global average. This has contributed to putting countries like Canada into a water crisis. And you say, how can a country like Canada have a water crisis? You've got 20% of the world's fresh water. Well, we still do. It's because of changing cold snow and ice processes, glacier loss through the north, diversions of rivers, flooding caused by glaciers in the Yukon, ice jam flooding throughout the country, shorter snow-covered seasons further south, contributing to wildfire, contributing to drought, the greater amount of rainfall in southern parts of Canada in the headwaters of rivers that flow into the Arctic have had extraordinary floods over the last 10 years. And then associated with this are undrinkable water for our Indigenous communities, longer ice-free periods of our lakes, contributing to harmful algal blooms and ecosystem collapse in the area. So lots of very unpleasant things occurring in Canada, and many of them in the far northern parts of Canada. You can summarize some of the impacts so far as that we're simply getting earlier melt and ice to water too soon. And so I'm going to illustrate some of these points using paintings from the artist Gennady Ivanov, who's artist in residence of Global Water Futures. Now, this is the Yukon River on April 23rd, 2019. It's already flowing. It was the second earliest breakup since records began in the 1890s. So looking forward, amplification of warming will be greater in the circumpolar north. And as the global temperatures rise to 1.5 to 4 degrees, according to models, we see much greater warming occurring at the higher latitudes, so more to come. So what can we expect? These shorter winters, earlier breakups, but changes to the hydrological cycle and intensification of that cycle in some areas that need investigation. So one we zoomed in on, this is a project that Rick Janowitz and Sean Carey and I worked on with graduate student Sebastian Crow. And this is looking at snow and ground thaw sensitivity to warming on the Dempster Highway, which connects southern to Arctic Canada through the northern Yukon into the Northwest Territories. And we looked at the sensitivity to warming using coupled hydrological models here. And what we found was that, interestingly, under warming climates, we would get lower snowpacks if precipitation did not change, but we would get much greater ground thaw through this. And so currently, we're seeing ground thaw of about from 0.9 to 1.3 meters, and we would expect this to increase to 1.5 to 2 meters in the future. We're already seeing these problems on the Dempster Highway with washouts occurring on a regular basis due to ground thaw and to extreme precipitation, often heavy rainfall. This cut off this Dawson City, Yukon, from the rest of the world earlier this autumn. So moving further north to the Inuvik area of Havoc-Pack Creek, we then examined using a similar, very strongly coupled snow hydrology permafrost modeling the impacts of the future hydrology. Havoc-Pack Creek is where the northernmost forests in North America meet the tundra. And so including a variety of processes in the model allowed us then under a future scenario of RCP 8.5, so late 21st century, using an atmospheric model called WRF, the Weather Research and Forecasting Model, which gave us 4-kilometer dynamically downscaled atmospheric inputs. Very important to get the precip right. And we bias corrected that for the current climate to the Inuvik observations that we had available. And the predictions are stunning and disturbing in this environment. We see the snow water equivalent going up by 80 millimeters, almost doubling by the end of the century in this environment, and a faster, earlier snowmelt occurring from that. So not the slower snowmelt in the warmer world, a faster snowmelt in the warmer world. We saw stream flow volumes increase by 100%. Peak stream flows more than doubling in this environment in the month of May. Evapotranspiration increasing, sublimation of blowing and intercepted snow decreasing, soil moisture increasing, peaks increasing, as I mentioned, snow cover duration dropping by about a month, and the melt rate of snow increasing 80%. Also, the increase in the active layer, the thawed layer of permafrost, by 25 centimeters. And so when we look at the future climate and at the thawed layer in this area going up to 1.3 meters. So very disturbing results from what has traditionally been a cold place. Here's a snow survey back in the early 90s with Professor Davies, Phil Marsh, myself, and others. And you can see it was a very snowy, cold place at the end of April. It will not be like that in a few decades. So some of this captured by the Arctic Canadi, even off impermanent frost, showing a permafrost slump in that area and the declining forest and the exposed ice that is now occurring. So what can we expect for Western and Northern Canada under these sorts of conditions? From our studies, we expect northern expansion of shrubs into the tundra. There's tremendous shrub expansion occurring already. Loss of evergreen needle-leaf forests due to fires and disease in the northern boreal forest. Expansion of broadleaf deciduous forests, aspens, willows, and others. Northward expansion of grasslands, so the prairies into the southern boreal forest. Of course, the decline among leaders occurring also tremendously quickly, and changes in agriculture in southern and central Canada as new crop varieties take advantage of warmer climates where soils permit, and soils usually don't permit much expansion. We expect a substantial increase in snowpacks in northern Canada, and we're seeing this in some degree, increased rain on snow flooding, expansion of drainage networks as permafrost collapses. We expect to see much of the decline of the permafrost coverage in the Mackenzie River Basin by the end of the century, even in areas that are continuous right now. The summer low flows will change. We expect irrigation expansion in the south and a dramatic increase in flows in the Mackenzie River Basin, going 1.5 times its current annual discharge, with a peak flow in the spring roughly 1 month earlier and doubling of peak flows. So the impact on infrastructure through northern Canada is going to be horrific with melting permafrost, thawing permafrost, increasing flood peaks. It's going to be tough for our highways in towns like Inuvik. In the Yukon, to try to find solutions for this adaptation, we have instituted a flow forecast system over an area 10% larger than the United Kingdom that is very sparsely gauged. This is using one of our models called MESH, driven by Environment Canada's meteorological forecast system. And we have implemented this. It came in very useful for Yukon government authorities in the past 2 years when record snowpacks in the southern Yukon, particularly the city of Whitehorse. So finally, I wrap up and say that it's not enough to create knowledge. We have to share and exchange this information. It has to be an iterative process between the users and the research community to ensure uptake of the research results, to involve the user community all the way along through the process, from the beginning all the way through to the end, and to take advantage of their tremendous knowledge, whether it be Indigenous or simply local, in terms of interpreting those results and finding solutions for moving into this warmer, wetter Arctic that we are moving into. So thank you. I will stop there. And thank you very much for having me here.
Thank you, John. Now we are over with the virtual speakers, and we have 3 speakers on site. So next up is Dr. Sean Marshall. Sean is a glaciologist and Canada Research Chair in Climate Change at the University of Calgary. He is the chair of the Cryosphere Working Group of the International Arctic Science Committee and co-chair of the WAFMO Global Cryosphere Watch Program. Dr. Marshall is currently seconded as the Departmental Science Advisor at Environment and Climate Change in Canada. He will be presenting the glacier and ice sheet response to climate change with a focus on Antarctica.
Thank you, Anna. I just realized this is turning into a kind of a Canada-Iceland joint session. I don't think it was intended that way, but it's my 2 favorite countries, so that makes me happy. But I will be speaking mostly about Antarctica here, which is I'm a little bit humbled to be speaking because it's not my research area. There's some Antarctic experts in the room, but there were some pretty interesting Antarctic ice sheet discussions at Cryosphere 2022, and my goal is just to summarize some of the things that were discussed there. I'm going to jump to this plot, and Thorstein showed us some of these glacier mass balance plots for Greenland and Iceland, and I think the Alps, but just to emphasize that this is really global. This is the World Glacier Monitoring Service glacier mass balance record from 1950 to 2021. You can see there's only 5 years in there of positive mass balance in the blue. So pretty clear signal from this composite of about 42 glaciers across the world. And you also see the real acceleration of glacier demise in this century. And this is really contributing to some of the acceleration in sea level rise. This is what it looks like on the ground from a site close to where I live, Athabasca Glacier in the Canadian Rockies. But you can see this scene kind of anywhere in these matched photos. It's pretty profound, the change of the ice melting kind of beneath our feet. And we heard from Thorstein about the Greenland and Arctic regions, and I'm not going to present those. I'm going to jump to Antarctica. But in work in the Arctic, it starts to look like this now, a lot more blue than white. And it should be more mostly just white with the sea ice. But this is kind of emphasizing to me how we're getting a lot of open water, how the warming in the air is combining with ocean warming to really get at some of these marine-based ice sheets, certainly in Antarctica, but also in Greenland and in Arctic Canada. So Antarctica is super interesting to me. And I think Chris this morning, who's one of the Antarctic experts in the room, has been talking about this a bit here yesterday in this pavilion, and referred to that as the kind of the sleeping giant. I think of it as the kind of elephant in the room that with the glacier changes and Greenland changes, we're certainly getting many decimeters of sea level rise this century, half a meter of sea level rise from these sources and thermal expansion. But Antarctica is this really big wild card, and we know that Antarctica has been losing mass from west. Trying to make that go. We know that it's been losing mass from West Antarctica in the past 15, 20 years or so, and very interesting studies around in the Amundsen Sea sector of West Antarctica. We're really, this is dominating Antarctic mass loss so far. And I think it's almost distracted us a little bit from thinking about that sleeping giant of East Antarctica. And I don't know, I've not been working in Antarctica for many years, but I used to do models of Antarctic ice sheet evolution. And maybe 20 years ago, I did modeling where I just really cranked up my iceberg calving, and I made most of East Antarctica go away. And I thought, oh, that's silly. And I stopped doing experiments like that. But that's kind of what people are starting to think about now. Like maybe that's not so silly. And that I hope it is, but it's the kind of thing that we really need to understand a bit better, is these processes of ice ocean interaction and potential ice cliff instability around the margins. And West Antarctica is certainly vulnerable to these kinds of instabilities. And we're starting to realize, I think, that sectors of East Antarctica might also be really vulnerable to this. And there are places here, this is from Eric Regnot's presentation at Cryosphere 22. There are places in East Antarctica where you are seeing some mass loss in recent years. Wilkes Land. If you actually go around the Antarctic continent and look at all the marine-based sectors of the ice sheet, this is again from Eric Regnot's presentation at Cryosphere 2022, you start to get into kind of scary numbers of how much ice could actually come out of Antarctica through ice ocean kind of destabilization of the ice sheet. And so West Antarctica, we're maybe already seeing the start of some of those processes with Thwaites Pine Island Glacier System, which has been called the Doomsday Glacier. But I guess the real concern is if that is a foreshadowing of what might be coming as the decades go along this century, if we start to destabilize major sectors of East Antarctica in a similar way. And Eric estimates that you could get 22 meters of sea level rise out of Antarctica over probably many centuries, but over these kind of marine ice instabilities. This calving process really is or marine ocean ice interactions. I mean, we've been talking about this for a while. Karen is doing work in this space. This really is one of the key uncertainties, and it needs a lot of really interesting and creative observations, I think, to actually treat the ice sheet as, more as a systems approach of the ice, ocean, sub-ice, shelf, atmospheric interactions, and understanding how these are interacting in the different water masses to really get at how quickly this can happen and how unstable this really might be. Is it potentially unstable? Is it really unstable? And there's a couple of different sources of instability that I won't talk about, but one is called the marine ice sheet instability, and it's kind of a tidewater glacier instability in a way, and that's what's playing out in West Antarctica, and that seems to be real. It's been pretty well understood and talked about for decades, and once this one starts, it can be difficult to stop, and hence the term the Doomsday Glacier. But this ice calving failures, ice cliff instability is I would say still in the realm of kind of hypothesis, frightening possibility, but we have seen major blocks come off. We've seen ice shelf collapses. It's not it's not something that's out of the realm of possibility with brittle ice physics. It's just a question of how systematic this can be. Are there positive feedback such that once this starts, will it keep going and really unravel and dig into East Antarctica? If we do start to see these kind of ice cliff collapses in East Antarctica, it's a really important area that we need to understand a bit better. And I think this kind of instability, even if it's kind of low risk, is such a high consequence that it needs a lot of really dedicated study. And you see it here with the potential sea level rise, this kind of potential future sea level rise scenarios. When you include these ice cliff instabilities, we get to kind of numbers that you don't see in IPCC. It's kind of order of magnitude higher over the coming centuries. And it's not glaciologically impossible. It's maybe low probability still, but I don't think we understand this well enough yet. And looking into the paleoclimate record, as Karen mentioned, you can see times like in the Eemian and the Pliocene where Antarctica may have looked like this, and global sea levels were 6 to 8 meters higher in the Eemian, or maybe 20 meters higher in the Pliocene, where probably East Antarctica had a big role to play in this. And what we don't know is maybe how long this takes. Is it 200 years or is it 2,000 years to actually go from the current East Antarctica to something that looks like that? And this has been shown a lot. Karen even mentioned this is the favorite slide of Cryosphere 2022. But I'm showing it here because Rob DeConto, who's done a lot of this work on the ice cliff instability and has been really slowly convincing, I think, many of us that this could be real. We need to be really thinking about this. Rob had this really interesting comment. Within IPCC, they note this is a low likelihood, high impact scenario, and that's the way I've been talking about it too. But Rob pointed out that deep uncertainty doesn't mean low likelihood. That's kind of an interesting thing to think about. If this is a structural process that's not in our models at all, we can't just run an ensemble of models and say that, what is the likelihood? Is this low likelihood or not? It's missing from our process models. So getting into a risk analysis framework to actually say, to put a probability on this is, I don't think we can do that right now. So just to wrap up, just to say that this really does matter, because if we're looking at 1 meter versus 5 meter versus 12 meters of sea level rise, then I think most of us to get here flew through Cairo, which will risk being underwater at some point in the coming centuries, and along with many other important lowland regions. And I think I lost my conclusion slides, but that's okay. I'm out of time, so off to you.
Thank you so much, Sean. Well, I'm the next presenter, so I already presented myself. My name is Anna. I'm head of the National Knowledge Center on Climate Change Adaptation in Iceland. I was also a key listener at the Cryosphere 2022 conference. And today I will reflect upon some of my following thoughts from the conference. On the impacts on nature and future scenarios. So I had a little bit different theme from Karen before. And I'll try to cover these points here on this slide. Here we see the global estimates of the changes for the components of the cryosphere, which data are accessible via the Copernicus data store. From the figure, we see that the annual cumulative ice sheet loss is estimated to be 372 gigatons per year, which is 8 times the volume of Lake Garda, and the annual cumulative glacier ice loss is 3 times the volume of the European Alps. That's 350 gigatons per year. And if we put that into perspective, that's the total volume of Vatnajökull over 10 years, for those that know the biggest Icelandic glacier. And here you can see how the permafrost limits move northward under the warming, and also graphs from Julia Boik from the conference showing the permafrost warming and in stations in Siberia and Svalbard. Permafrost contains organic soil that's been building up for thousands and thousands of years. It's a fossil carbon pool that hasn't been part of our system for so long, many thousand years. And also, I'm not going to dwell long on the science in that sense, but here you can see the Arctic ice sheet and the Greenland ice sheet combined in one slide. The Greenland ice sheet has lost over, on average, 212 gigatons over the past decades. And up until now, like I think Sean mentioned, it's been the largest contributor on the glacial meltwater to the risen sea level during this period. The Greenland ice has lost what equals 1 Hofsjökull for every year for the past 20 to 30 years. That's also an Icelandic reference, but I see many of you are Icelanders here, so maybe you know. But then we have the Antarctic ice sheet. Sorry, that's what Sean came into. That has lost 150 gigatons per year since 2000. But like we've heard today, scientists believe that it might be catching up with Greenland. And there is an increased worry about the instability of West Antarctica. Okay, but why is the cryosphere so important? Why do we even care that the glaciers are melting? Why does it matter that the Arctic is warming faster than the rest of the globe? Ice on land in the form of ice sheets and glaciers plays an important role in the Earth system through its ability to store vast amount of water away from the oceans for a long period of time. Any change in the ice volume stored on land has a direct impact on the global mean sea level. The cryosphere is a deeply interconnected system in itself, but also a system that is deeply connected to the rest of the Earth systems. It is very sensitive to feedback loops, and I could actually give you many examples, but I'll stick. If you look at the permafrost, because I mentioned that earlier, there is so much carbon stored in the permafrost, and it's frozen now, locked away, but when it thaws, it becomes vulnerable for being released into the atmosphere and exacerbating the global climate change, creating this vicious cycle. And another example is the fact that the cryosphere exerts an important influence on the Earth's climate, owing to its high surface reflectability called the albedo. This property gives it the ability to reflect a large fraction of solar radiation back into space and influences how much solar energy is absorbed by the land and oceans. Experts suggest that there might be nearly no sea ice in the Arctic summer by the late 2030. Let's just imagine that there's no sea ice at any given year. Instead of the Arctic to be white and icy, it becomes expansive dark ocean. And dark ocean absorbs even more sunlight, warming the Earth even faster than it is now. Most of you are probably familiar with this saying, what is happening in the Arctic doesn't stay in the Arctic. But what does that really mean? Changes that happen in one location of the Earth resulting in a different geographic location. It is often also called teleconnections. An example of such would be the relationship between the warming in the Arctic and the changing patterns in the jet stream. And that matters because the jet stream has a lot to do with weather patterns we experience in so many places. So what does the future look like? Will all the glacier join our Ok glacier, also an Icelandic reference, but that's a glacier that has already been declared dead. We now have a clearer picture of the past, present, and the future than ever before. Scientists might have slightly different theories about the pathways, but they agree on the big picture. The ice is melting and will continue to do so. And according to IPCC, unless there is immediate reduction in greenhouse gas emissions, limiting warming to 1.5 and well below 2 degrees will be beyond reach. In Iceland, Vatnajökull, our biggest glacier, is modeled to lose 15 to 30% by 2100, Hofsjökull 60%, and Langjökull 90%. So, to go back to that question, what does the future really look like? It looks like a future that we really need to adapt to. Which brings me to my final question. What kind of climate services does this current and future state of the cryosphere trigger? Part of the services we need to relate to communication and the right information. We need to know the current state of the cryosphere through observation and monitoring. We need standardized observations for the cryosphere. We need to know how the future looks like based on the best available information, and we need to have the most relevant regional information available, accessible and understandable, both for the policymakers and for the science community. And for the public. We need downscaled information, what is relevant for each country with risk assessment, and we also need to be open to use the opportunities. But last but not least, the climate service need to include science communication. The scientists need to be involved, but the responsibility to run such efforts should not solely rest on their shoulders. As for the direct impacts of melting cryosphere, we can see the changes in the glacial mass and runoff, rising sea level, isostatic uplift, landslides and floods, and all of these impacts result in increased risk that we need to be prepared for. The Arctic permafrost thaw, for example, and the profound hydrological changes can cause disruption for transportation and supply chains and damage to infrastructure. If we go back to Iceland a bit, Iceland is being located at the confluence of the North Atlantic and the Arctic Ocean, and Iceland is prone to a multiple of hazards, including extreme storms, floods, earthquakes, even volcano eruptions, landslides, and avalanches. But climate change is contributing to a shift in the magnitude and scale of hazards and the emergence of risks in areas where they were previously unknown. As an example of hazard due to the melting glacier is a hazard in the southeast of Iceland. A fracture in the mountain slide of Svínafellsheiði threatens to cause between 60 and 100 million cubic meters of rock to fall onto the glacier below. A large landslide could break off the surface of the glacier and crash onto the proglacial lake and affect the people and the infrastructure downhill. We need to adapt to those changes and become more climate resilient. But adaptation also means that we should prepare to embrace the opportunities when they occur. So, in conclusions, I want to mention as a whole picture kind of message that it is not enough to look at the previous IPCC reports and carry out our understanding that the melting of the cryosphere and its effect on the polar regions are as an early warning signals. At this point, they are driving climate change and impacts globally. And with this, I will conclude my talk and present the next speaker. Wait, I'm gonna introduce you, Dagfinnur. Dagfinnur Sveinbjörnsson, he is the next speaker. He is the Arctic Circle emissary on the third pole, climate and the oceans. He is the founder and the chairman of the Climate Research Foundation and former Arctic Circle CEO. He has for a number of years worked efforts to initiate and sustain regional and international collaboration on scientific research on the nature and consequences of climate change with a focus on the Himalaya third pole and the Arctic. He will present to us a collaboration on scientific research in the third pole region. Thank you.
Thank you very much. So listening to these earlier presentations, there are several themes that have been touched upon repeatedly. So first of all is the state of the cryosphere. Is the microphone, is this okay? Or okay. State of the cryosphere in general, and the relationship uh, with policymaking authorities, and how scientific findings need to be communicated so that they can feed into deliberations contributing to policymaking. And we have also discussed hazards and risks, and teleconnections. And I will touch upon all of these and do so for items. I will consider third portion. I will talk about the R model and Himalaya, the Hindu Kush Himalaya Assessment Report, and the third pole process. And to take it to the third pole region, first of all, in order to kind of motivate this discussion, I would like to put this in a bit of a historical example of how things have evolved over the last 15 years. In early October, there were two articles within 2 days in the New York Times, and both of them were on the Indian monsoon and how the monsoon was behaving in a very unpredictable manner, and how it was creating catastrophic conditions for the possibilities of food production in South Asia. And several days later, there was a special session celebrating a publication of a special issue of Nature, which was devoted to the Tibetan Plateau. And all of this I find may seem very simple, but it's still very interesting, because 15 years ago, when the IPCC report was published, 2007, the third pole region, as we see here on the screen, was referred to as a white spot. And it was referred to as a white spot, not because it's the contains the largest reservoirs of fresh water outside of the polar regions, but there's a term that referred to the lack of data. So it was a way of saying we simply do not know what is the state of affairs with regards to the cryosphere in the third pole region. And this was then also repeated in a report 5 years later in 2012 by the United Nations Environment Program, emphasizing that there was a serious lack of data on the Himalayas and the surrounding mountain ranges. So in other words, we cannot make conclusions and inferences as to what is taking place with regards to the cryosphere, the melting of the ice, and what the consequences will be for the water resources across Asia. And now taking us back to 2019, we have two publications. Yao Tongdong, the foremost glaciologist of China, in an article in Nature, predicted that 2/3 of the glaciers of China would disappear by 2050. And in the Hindu Kush Himalaya Assessment Report, published in 2019 as well, it was predicted that more than half of the 56,000 glaciers of the Hindu Kush Himalaya and the third pole region would disappear by 2100. So in other words, pretty dire predictions in terms of the melting of the ice. But that leaves the question: what are we to make of these information? That people are very often jump to statements about the very serious consequences for hundreds of millions of people downstream, up to 2 billion people. And if you add up the populations in the major river deltas of the region, then you're very quickly over 1 billion people, with the Yellow River sustaining life for 150 million, the Yangtze 370 million people, Indus 320, the Ganga Brahmaputra region 670 million people, and then we are not even talking about the Irrawaddy, Mekong, or the rivers of Central Asia. And but the need for further research has been very much on the variations across the region. So it's very difficult to generalize as to what will the effects be across this extremely complicated region. And that's where I want to add some information. And these are kind of slides that are based on relatively recent scientific research. And so if we look at the variations across the third pole region, then we can see, of course, that the Tibetan Plateau and the third pole region is warming faster than the global average. And it has also, there are indications that the warming is taking place fastest in the Karakoram region, the Hindu Kush and Pamir. And this then is also supported by satellite data and other data that confirms that the mass balance loss of the glaciers is most pronounced in the headwaters of Indus and around the Brahmaputra's Big Bend. And this is very significant because these are also the regions that are most important with regards to food production, the Indus irrigation system being the largest irrigation system on the planet, and the region around Brahmaputra's Big Bend is also a region of fundamental importance for the big populations of Bangladesh and the Bay of Bengal and the river deltas of Ganga and Brahmaputra. And at another level, it's also very important because these are the parts of the region which are most sensitive with regards to geopolitical tensions. And so this is one point, the variations across the region. And then there are the added complications of what else is taking place, what else is affecting the consequences of melting ice and glaciers. And scientists are now working on the kind of mapping how precipitation patterns need also to be studied and to kind of substantiate this picture. And as Walter Immersiel has demonstrated, because of climate change, the water cycle becomes more rapid, and even if the ice is melting, we may not be running out of water that quickly. And that pattern, the more rapid water cycle and the variations across the region in terms of the melting in the cryosphere is something that needs to be studied further and scientifically better established. And so the most fundamental consequence is not necessarily the changes in the the river flows and the water resources, but with the disasters and risk hazards that are caused by climate change in the region. And just to show you this very quickly, then as you can see, the areas in the region that are most prone to hazards and risks will be the regions where the warming is taking place faster than elsewhere, and where the consequences for in major river deltas of Indus and Brahmaputra, and there you have the kind of combination of floods, landslides, and and variety of other hazards. And here you can see the pictures of the floods in Pakistan in August this year, and in Uttarakhand, India, in February 2021. And going back to the Hindu Kush Himalaya Assessment Report, then this is the most comprehensive assessment report that has been prepared on the region. And the takeaway from this report, establishing these variations and complications, is that call to action, that there's a need for immediate and decisive action and renewed efforts to communicate the gravity of the challenge to the political and policy-making establishment of the region and beyond. And that brings us to the dialogue with the policy-making establishment and the communication of scientific knowledge. And there we have sometimes referred to the Arctic model of collaboration as an inspiration and as a model. And we recently launched what is referred to as the third pole process, which helps to take the dialogue beyond the purely scientific and to engage the decision-making authorities, policymakers, and also to do so in a comprehensive way, including a host of different kinds of information. And so there you can see the journey as it will be in the coming months. The next stop will be the Abu Dhabi Sustainability Week, the Arctic Circle Abu Dhabi Forum, and then in Tokyo, Japan in early March. And this will then be integrated into the preparations for the COP28 or the Emirates Climate Conference towards the end of next year. Thank you very much.
Thank you so much, Dagfinnur. And now for the final part of the event, I want to invite our panelists to join me up on the stage, Dagfinnur and Sean, and also Dr. Johan Stander. And I've already introduced all of the panelists except for Johan. He is the director of the service department in the WFMO Secretariat since August 2020. And he has been working in close collaboration in support to support the activities of the Service Commission of WFMO. Before joining the WFMO in August 2020, he worked for the South African Weather Service. And he has also studied meteorology and holds a PhD in oceanography. And he first served WFMO as of 2005 when he was elected to the Executive Council Working Group for the Antarctic Meteorology. So, I will start with you, Johan. The scientists have reiterated that the impacts of the melting cryosphere are felt in polar and mountain regions, but also downstream on lowlands and small islands. How can WFMO bridge between science and operation to meet the increasing demand for sustained, timely information on the impact of changes in the cryosphere, regionally and globally?
Excellent. Can you?
Yes.
All right, I'll have to keep this very close. I think this is almost similar to the other panel we had earlier this morning, and I'm going to repeat the same words. I think it's high time that we start in where we've got a lot of people doing research on certain areas, but not necessarily sharing that with those people who really do the negotiations. We've got a research board, and we've got then the Services Commission, which develops the required technical requirements for us to provide services, in particular climate services. And then we've got the Infrastructure Commission, where all of this, they look after the data part, where all of this are integrated. Then We take this through the commission sessions and then also through the Executive Council and Congress. Then once approved or through a resolution or a decision is then for the members to implement, and it can be monitored. So I think I need to start with that particular aspect. That's very important. The second point I wish to raise is that looking at a strategic point, we've really made sure that from the WMO side that it's important. And I think someone mentioned it earlier today, it's almost too late. I think the minister said it's almost too late, but it's never too late. Let us at least start somewhere. And looking then at the strategic plan, we've set up a specific branch within the services department looking after water, hydro, and cryosphere because they're all interlinked. And in our strategic plan for 2024 up to 2027, there's a specific element in the strategic plan that deals with the changes of the cryosphere, the impacts of that, not only for those people living up in the mountains, but the downstream effects with regards to sea level rise, floods, storm surges, and all of those that it's just immense. And then looking particularly at sea level rise and the statistics we've seen from the presentations this afternoon, as the sea level rise, then those people at small island states are then at risk. We often talk about those around the coast, but what about the small island states? There won't be a small island anymore if we don't do anything about it. What about those people? They don't want to leave their island. So it's a real threat for those people. And then I think when the UN Secretary General Guterres requested or announced on the 23rd of March that he would like everybody on the planet to be protected by early warning systems in 5 years, requesting the WMO to lead the development of an action plan to be presented at COP was a once in a lifetime opportunity. And in that 5-month period, we've really worked extremely hard with fellow UN partners, with research, academia in particular, private institutions, funding agencies, and our national meteorological and hydrological services to put this high-level action plan together, which was then launched last week with massive support from members or countries, UN partners, and everybody that helped us developing this. In that particular action plan, and if you haven't seen it, please go and read it, because that's just high level. There are aspects of high mountains, cryosphere, the Antarctic and everything around it. So it's in there. And everything that we will then deliver within the next 5 years got to be around these things. From the observation, research and services part, through to the disaster risk reduction part, through the communication part, through the preparedness and response. All 4 pillars for a people-centric one. And this is extremely important. And we cannot do this alone as an organization. And that's why he did not say the WMO must own it, he said he must lead it. Therefore, we'll have to get everybody together to implement the action plan when we do that in the following years. Looking further at the WMO, we've got the regional climate centers and regional hydrological centers, and we've also established the Arctic regional climate network, and hopefully by December they'll establish the Antarctic regional climate network. And that's also important. So all of this is where we get information, we get climate, we get everything that we need for the people to use. So if we've got academia out there and you're sitting out there and you're not sharing your data, please share it with your National Meteorological Hydrological Service so that it can be incorporated in the national, in all our numerical weather predictions through our centers so that it can go back to you so that you can use the data globally for the same process going forward. Thank you.
Thank you very much. Dagfinnur, I want to ask you, what do you think are the main political challenges for the third pole and the Himalaya from a local perspective?
Well, first of all, I should say that it's very sensitive to talk about politics in that region in the first place. So I will simply point to two very prominent complications, which also relate to my presentations on the 2 points on the map that I was primarily drawing attention to. I mean, first of all, it's of course complicated that where we have these scenarios where one country controls the headwaters of another country. So, for example, when India controls the headwaters of the Indus and for Pakistan and can theoretically very much affect the water flow into Pakistan, and of course in the region around the Brahmaputra's Big Bend, where China really controls the headwaters of Bangladesh and India, and so obviously you have a very extremely complicated political situation in those kind of contexts, and then of course you have variety of other complications of a political nature across the region, which would be too long of a speech to talk about.
Thank you. Sean, what do you believe is the main scientific challenge in cryospheric research?
How much time have we got? No, I actually really liked Karen's summary of some of the directions, and I think she pointed out the kind of need to really work together a bit better on some data sets and data coordination, and within Global Cryosphere Watch, there's work to do to really operationalize and get that data flowing and available, for instance. But I think in my time as a glaciologist, I've seen so much progress in this direction with kind of community modeling and projects like the Randolph Glacier Inventory, Glacier Analysis for the World. I think Fabian's gone now, but the OGGM, the Open Global Glacier modeling work that he's done, there's amazing community developments in our field. So it's come a long way, and I think we need to just go a bit further in that data direction. Another thing I might kind of come off of Karen's point was she brought in the technology and how that's opening up a little bit more opportunity for diversity within the community, and that's come a long way too, I have to say. And that was a really interesting observation that I think is much more accessible and diverse to be in our cryosphere community, and that coming by the Cryosphere Pavilion a lot over the past week, that's really evident, and I think that's really good progress, and that will help our science along too. So we need to keep moving in that direction. And then on the kind of science side, I guess, I would say that I almost feel like some of our models are a little bit ahead of our science, if I can say it that way. The models have really embraced Earth system modeling approaches. We now have unified models that go across the continuum of time scales. And I think we've seen the cryosphere arrive as part of the climate system, but a lot of us are still doing disciplinary work. It's kind of natural. I think a lot of our observation systems are done, the different components of the climate system, they're not integrated. Research studies can be the same way. So I think a more integrative approach in the actual, some of the research, some of the monitoring and observations. I'm working right now with Environment Canada, and we've got different teams going up to measure the water quality and the water quantity and the atmospheric chemistry and the soil quality and the glaciers and the permafrost. It's all different groups. It's just not brought in and coordinated the way that we need to be thinking of it as an actual Earth system approach. And the models are kind of there, but to be informed by the right processes and feedbacks and interactions, we almost need the science to catch up a bit. And I think that's part of what's going on with the East Antarctic challenges too. I'll maybe stop there.
Thank you. We don't have much time left. I'm gonna shoot just very quickly. Sean, what do you think are the main research gaps in this term? What do you think are the main research gaps? In very few words.
Yeah. I mean, I think that integrative approach is really a big one, and I think I don't know. There's so much interest and attention and importance to the Antarctic right now that I think it would be really nice to see an international effort. I'm interested in how we can piggyback onto the early warning systems that you've mentioned, because this is the real opportunity that it really involves cryosphere in a lot of places, it involves kind of the operational through to climate time. So maybe it's a way we can think about, in a strategic way, how do we introduce better observation monitoring systems that really fill in some gaps. And the Antarctic and Southern Oceans are pretty big gaps within that.
Thank you. One for each of you. Dagfinnur, what do you believe are the main challenges for research collaboration in the third pole, and has there been any progress since you started monitoring the situation? Oh, the microphone is...
I may begin by commenting the progress that has taken place. So, as I alluded to or discussed in a presentation, in 2007, so 15 years ago or so, I had the situation was such that major publications were saying that we don't we cannot really judge what is taking place with regards to the cryosphere in the third pole region. And of course, if we do not know what is taking place with regards to the cryosphere, we cannot really make judgments about what the consequences will be for the water resources and rivers downstream. And if I may then take that as a major research challenge, referring to the comments that were made earlier about this holistic nature of the research challenge, that is to say. So if we look back at those years when we simply didn't have data, about the region itself or the mountains and the glaciers, and now we or the scientists are beginning to establish what the variations are in the region, and therefore what the implications are for different river deltas and what the consequences are. But then it turns out, which is so remarkable, that because of the holistic nature of the weather systems of the planet and the teleconnections, it becomes impossible to establish what the results will be unless you have data from the Arctic, because the melting of the sea ice is very much affecting the behavior of the monsoon wind, which I commented on in the very beginning of my presentation. And if you cannot or get a clear picture of what the behavior of the monsoon winds will be, then it will be very difficult to establish any holistic judgments of what the consequences of the melting of the ice will be. So if I may simply place that on the table for people to think about, how complicated this is. So it's not only about the ice or the water, it's about the whole weather systems.
Thank you. And for the final question, Johan, you kind of touched upon this before, but if you could sum it up, how you foresee the future of the WAFMO's Global Cryosphere Watch in support of weather, water, and climate services?
I think the establishment of the Global Cryosphere Watch is really fantastic. I think it really bridges that gap between the operational cryosphere people, the International Cryosphere Committee or community, and the operational side, which is the WMO and its members. And I don't think that has ever been there before. And that's critical. It needs to be integrated. It goes back to my first comment. We need to work together going forward. With that in mind also, if we see what they've done with the first speaker, and I'm going to try and pronounce his name because I don't know how to do it. Poston? Yep. First time? Okay. So Poston was one of the lead authors in the Glacier Measurement Best Practices Guide. We spoke about best practices, and this is what we need. And that was done, and we're moving forward with that. The second one I want to mention is the, I think, with the specialized cryosphere products that will be then become available, it's important because it will be available for everybody as it can be shared. Then the last I wish I could, I don't know if he's online, but we all need to recognize Arnie of the National Meteorological and Hydrological Service. He's been a very strong advocate for the cryosphere and the third pole. and it's time. And I think one day when he retires, I think he'll be able to say, I've left a legacy. You know, it's there in the WMO programs. We've done something. And Arnie, all the best. See you one of these days. Thank you.
Thank you. I will reference Árni Snorrason. Thank you. Now we are done with the time, so thank you very much for joining and participating, and for you audience. And yeah.